Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. Before we begin, I'd like to give a special shout out of thanks to some new members of our Patreon family: Sarah, Mari, Anna, Barbara, and Maida. Thank you all so much for supporting this podcast. By becoming members of Patreon, you help us remain 100% listener supported and ad-free for everyone, and it's very much appreciated. If you are interested in supporting Boring Books for Bedtime and finding out more about the perks available to subscribers, including exclusive episodes heard nowhere else, you'll find a link to Patreon in the show description. You'll also find a link to buymeacoffee.com, where you can support us with a one-time tip, no subscription required. I hope you'll take a moment to check them out. Now, let's read and relax. Find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight, let's continue our exploration of our universe with more from Astronomy for Young Folks by Isabel Martin Lewis, A.M., connected with the Nautical Almanac Office of the U.S. Naval Observatory, and first published in 1922 by Duffield and Company, New York. Let's pick up right where we left off, exploring our own planet. Let's begin. Chapter 24: The Earth as a Magnet. If a small, freely suspended compass needle is moved over a highly magnetized steel sphere, it will be seen that it constantly changes its position, both horizontally and vertically, so as to lie always along the lines of force of the sphere. There will be one point on the sphere, which we will call the North Magnetic Pole, where the north-seeking end of the needle will point vertically downward, or make a dip of 90 degrees with the tangent plane. At the diametrically opposite point on the sphere, called the South Magnetic Pole, the opposite end of the compass, the south-seeking end, will point vertically downward, while at a point midway between the magnetic poles of the sphere, the needle will lie parallel to the diameter connecting the two poles, and there will be no dip. The total intensity of the magnetic field surrounding the sphere will be found to be greatest in the vicinity of the magnetic poles, and least midway between the poles. Now, a freely suspended compass needle carried to all parts of the Earth will behave very much in the same manner as the needle moved over the magnetized steel sphere. There are 2 points on the Earth's surface, known as the North and South Magnetic Poles, where the needle points vertically downward, and approximately midway between is the magnetic equator, where the compass needle places itself in a perfectly horizontal position, and the dip of the needle is 0. In other words, the Earth acts as a huge magnet and possesses a magnetic field with lines of force converging towards its poles, similar to the lines of force of the steel sphere. There are, however, some very important differences between the sphere of steel and our Earth. The matter of which the Earth is composed is not homogeneous. It is believed to possess an iron core of considerable size, it is true, but its outer shell is composed of heterogeneous masses that in certain regions cause very appreciable local deflections of the needle. It is surrounded, moreover, by an atmosphere permeated by electrified particles of matter shot forth from the sun, which we now know is a still greater magnet, surrounded by a magnetic field that is of the order of 50 Gausses at the poles, and about 80 times more powerful than that of the Earth. It is now a well-established fact that the sun's magnetic field exerts a powerful influence over the condition of the Earth's magnetic field, and that vast solar disturbances affect very materially the direction and intensity of the lines of force. It is thus little wonder that this non-homogeneous and rapidly rotating terrestrial globe, surrounded by an electrified atmosphere, and subject to the action of a still more powerful magnet, the sun, should not behave in a manner exactly analogous to a uniformly magnetized steel sphere. The Earth's magnetic poles are neither symmetrically placed nor absolutely fixed in position. There is every reason to suspect that they shift about from year to year, and possibly fluctuate irregularly in position in the course of a few days or hours under the influence of disturbing forces. The position of the Earth's north magnetic pole, last visited by Amundsen in 1903, now lies approximately in latitude 70 degrees north, longitude 97 degrees west. The position of the south magnetic pole, according to the latest determinations, is in round numbers in latitude 73 degrees south and longitude 156 degrees east of Greenwich. It is evident, therefore, that the magnetic poles of the Earth are not symmetrically placed, and that they lie fully 30 degrees from the geographical poles. The cord connecting the magnetic poles passes 750 miles from the Earth's center, and it is about 1,200 miles from the geographic pole to the nearest magnetic pole. There exist, moreover, in high latitudes, local magnetic poles, due possibly to heavy local deposits of ore. One such pole was discovered at Cape Treadwell, near Juneau, Alaska, during Dr. L.A. Bauer's observations there in 1900 and 1907. In the center of the observing tent at this point, the needle pointed vertically downward, and the compass reversed its direction when carried from one side of the tent to the other. It is a well-known fact that there are very few points on the Earth's surface where the compass needle points either to the true geographical pole or to the magnetic pole, and if it does chance to do so, it is a transient happening. The variation of the compass, or the declination of the needle as it is called, is the angle that the compass needle makes with the true north and south line, or the meridian. It is an angle of greatest importance to navigators and explorers, for it gives them their bearings. Yet it is unfortunately subject to ceaseless variations of a most complicated nature, since it depends on the constantly pulsating and never-ceasing magnetic changes that sweep over the surface of the Earth and through its crust. It is affected by long-period or secular changes, as they are called, progressing more or less regularly in obscure cycles of unknown period. It is subject to a diurnal change that depends on the position of the sun relative to the meridian, and that varies with the seasons and with the hour of the day. It is affected by the sunspot cycle of 11.3 years, which has a direct effect upon the intensity of the Earth's magnetic field. The intensity of the magnetic field in sunspots is, according to Abbott, sometimes as high as 4,500 Gausses, or 9,000 times the intensity of the Earth's field. At times of maximum spottedness of the sun, the intensity of the Earth's magnetic field is reduced. Moreover, when great and rapidly changing spots appear upon the sun, electrified particles are shot forth from the sun with great velocity and in great numbers, and are drawn in towards the magnetic poles of the Earth. Meeting the rarefied gases of the Earth's upper atmosphere, they illuminate them as electric discharges illuminate a vacuum tube. Some of these electrons are absorbed by gases at high elevations. Others descend to lower levels. The most penetrating rays have been known to descend to an altitude of 25 miles, which is about the lowest limit yet found for auroral displays. It is the passage of these rays through the atmosphere that cause the magnetic disturbances known as magnetic storms that are associated with the appearance of great sunspots and auroral displays. At such times, sudden changes take place in the intensity of the Earth's magnetic field that cause the compass needle to shiver and tremble and temporarily lose its directive value. These magnetic storms have been known to produce great temporal changes in the intensity of the Earth's field. According to Dr. L. A. Bauer, director of the Department of Terrestrial Magnetism of the Carnegie Institute of Washington, the Earth's intensity of magnetization was altered by about 1/20th or 1/30th part by the magnetic storm of September 25, 1909, which was one of the most remarkable on record, and the Earth's magnetic condition was below par for fully 3 months afterwards as a result. In addition to these various regular and irregular changes in the variation of the compass, or declination of the needle due to changes in the Earth's magnetic field as a whole, there are local effects due to restricted regional disturbances of the Earth's magnetic field, or to local deposits of ore, or to volcanoes, or other local causes. The effect of all these disturbances upon the declination of the needle must be determined by continual magnetic surveys of all portions of the Earth's surface. As a whole, the Earth's magnetic field is more uniform over the oceans than over the land, with all its disturbing topographical features. Yet this advantage is offset largely in navigation by the fact that every steel ship that sails the seas is a magnet, with its 2 magnetic poles and its neutral line, where the 2 opposite magnetic forces are neutralized, as is the case with every magnet. The direction in which a steel ship lies with reference to the Earth's magnetic field while it is being built determines the position of the magnetic poles in its hull and the position of its neutral line, and this distribution of magnetism over a ship's hull must be taken account of in the installation of its standard compass. Every piece of horizontal and vertical iron aboard ship has an effect upon the variation of the compass, and compensation must be made for such disturbing forces. The direction of sailing, the position in which a ship lies at dock, storms encountered at sea, the firing of batteries on warships, are some of the factors that are operative in producing changes in the variation of the magnetic compass aboard a ship. Every ship must undergo at frequent intervals magnetic surveys for the purpose of determining its magnetic constants and its table of deviations of the compass. The direction in which the compass needle points aboard ship is the resultant of the effect of the Earth's magnetic field and the magnetic field of the ship, and both fields are subject to continual and complicated variations from year to year, from day to day, and even from hour to hour. The elements of the Earth's magnetic field are determined for any one epoch by long-continued magnetic surveys carried on to a greater or less extent by the various nations of the world, and the results are published in the form of magnetic charts for land and sea, showing the values of the three magnetic elements: declination of the needle, dip or inclination, and horizontal intensity of the Earth's field for a definite period. So rapid are even the long-period changes in the Earth's magnetic field that a magnetic chart can be relied upon for only a very few years, and fresh data for the construction of these charts that are so valuable to navigators and explorers must be gathered continually. The Department of Terrestrial Magnetism of the Carnegie Institute of Washington is engaged in continual magnetic surveys of the Earth by land and sea that are of the highest value not only to navigators but also to scientists interested in solving the great and mysterious problem of the underlying causes of the Earth's magnetism. To give an idea of the extent and scope of the work of this department, it may be mentioned that its non-magnetic ship, Carnegie, made in the period 1909 to 1918 a total run of 189,176 nautical miles, nearly 9 times the Earth's circumference, with an average day's run of 119 nautical miles. Magnetic observations were made practically every day at a distance of 100 to 150 miles apart. In this 9-year period, 5 cruises were made. On her first cruise, the Carnegie sailed from St. John's, Newfoundland, to Falmouth, England, over practically the same course followed by the famous astronomer Halley in the Paramour Pink 2 centuries earlier to determine the variation of the compass. In her 4th voyage, the Carnegie circumnavigated the world in sub-Antarctic regions in 118 days, a record time. She has traversed all oceans from 80 degrees north to the parallel of 60 degrees south, and has crossed and recrossed her own path and the path of her predecessor, the Galilee, many times, thus making it possible to determine for the points of intersection the secular changes in the magnetic elements. After a thorough overhauling in 1919 and the installation of a 4-cylinder gasoline engine made of bronze throughout to take the place of the producer gas engine used on earlier cruises, the Carnegie started on her 6th cruise with a crew of 23 officers and men on October 9, 1919. A cruise of 61,500 miles was planned in the South Atlantic, Indian, and Pacific Oceans to last approximately 2 years. Unsurveyed regions in the South Atlantic and Indian Ocean were to be covered, and the route was planned so as to obtain a large number of observations of the progressive changes that have taken place in the magnetic elements. This is accomplished as stated above by intersecting former routes and obtaining new values of the element at the points of intersection. In addition to its ocean magnetic surveys, the Department of Terrestrial Magnetism also carries on extensive land surveys in all parts of the globe. In 1919, special expeditions were sent out by the department to observe the total solar eclipse of May 29th at stations distributed over the entire zone of visibility of the eclipse and immediately outside. At Dr. Bauer's station in Liberia, the total phase was visible in a cloudless sky for more than 6 minutes, which is very close to the maximum length of phase that can possibly be observed. Unmistakable evidence was gathered at all stations of an appreciable variation in the Earth's magnetic field during a solar eclipse, which variation is the reverse of that causing the daylight portion of the solar diurnal variation of the needle. In addition to the magnetic survey work on land and sea, which is the chief work of the Department of Terrestrial Magnetism, atmospheric electric observations are carried on continually on land and sea, and experiments have been carried on at Langley Field, Virginia, in the development of methods and instruments for determining the geographical position of airplanes by astronomical observations. There has also been recently formed under this department a section of terrestrial electricity. The cause of the Earth's magnetic field is still one of the greatest unsolved problems of astrophysics. The theory that has been advanced by Schuster that all large rotating masses are magnets as a result of their rotation has received considerable attention from astrophysicists, and attempts have been made to prove this experimentally. It has been found that iron globes spun at high velocities in the laboratory do not exhibit magnetic properties. This may mean simply that the magnetic field is too weak to be detected in the case of a comparatively small iron sphere spun for a limited period under laboratory conditions. It must be remembered that the Earth has been rotating rapidly on its axis for millions of years and is, compared to terrestrial objects, an extremely large mass. Yet it has been shown that as a whole, our Earth is an extremely weak magnet, and that if it were made entirely of steel and magnetized as highly as an ordinary steel bar magnet, the magnetic forces at its surface would be 1,000 times greater than they actually are. If it is true that all rotating bodies are magnets, then all the heavenly bodies, planets, suns, and nebulae are surrounded by magnetic fields. We know nothing to the contrary. In fact, we know this to be true for the Earth and Sun, and strongly suspect that it is so in the case of the planets Jupiter and Saturn. When we understand more about the properties of matter, the nature of magnetism as well as of gravity may be revealed to us. Chapter 25. Some effects of the Earth's atmosphere upon sunlight. It is impossible to exaggerate the importance of the atmosphere to all forms of life upon the surface of the Earth. If there were no atmosphere, there would be no life, because it is through the agency of the water vapor, carbon dioxide, and oxygen in the atmosphere that all life processes are maintained. If there were no atmosphere, there would not only be no life upon the Earth, there would be also none of the beautiful color effects produced by the passage of sunlight through the atmosphere. There would be no blue skies, no beautiful sunrise and sunset effects, no twilight, no rainbows, no halos, no auroral displays, no clouds, no rains, no rivers nor seas, no winds nor storms. The heavens would be perfectly black, except in the direction of the heavenly bodies, which would shine as brilliantly by day as by night. To understand how the atmosphere produces color effects such as blue skies, sunrise and sunset tints, rainbows, and halos, as well as the twinkling of the stars and numerous other phenomena, we must know something of the nature of light itself. Light moves outward from any source, such as the sun, in all directions radially or along straight lines, so long as it does not encounter a gravitational field, with the unimaginable velocity of 186,000 miles per second. As it advances, it vibrates or oscillates back and forth across its path in all directions at right angles to this path, unless it is plain polarized light, in which case its vibrations are confined to one plane only. These vibrations or oscillations of light take the form of a wave-like motion, one wavelength being the distance passed over in the time of one vibration, measured from crest to crest or from trough to trough of adjacent waves. We may consider that a beam or ray of sunlight is made up of a great number of individual rays of different wavelengths and different colors. The average wavelength of light, the wavelength of the green ray in sunlight, is about 1/50,000th part of an inch. That is, it would take about 50,000 wavelengths of green light to cover a space of 1 inch. Now, since light makes one vibration in passing over a distance of one wavelength, it makes 50,000 vibrations while advancing 1 inch, and since it advances 186,000 miles in 1 second, we can easily figure out that a ray of sunlight of average wavelength makes about 600 trillion vibrations in a single second. The chief colors of which sunlight or white light is composed are red, orange, yellow, green, blue, indigo, and violet, though there are an infinite number of gradations of color which blend into one another, gradually producing the intermediate tints and shades. The colors just mentioned are called the primary colors of the solar spectrum, which can be produced as a band of light of variegated colors, arranged in the order named by passing a ray of ordinary sunlight through a glass prism. The individual rays of different color and wavelength that make up a beam of sunlight, or white light, then separate out in the order of the wavelengths. The red rays vibrate the most slowly and have the longest wavelength of all the rays of the visible spectrum. About 400 trillion vibrations of red light reach the eye in 1 second. Violet rays, on the other hand, vibrate the most rapidly of all the visible rays and have the shortest wavelength. About 800 trillion vibrations of violet light reach the eye every second. The wavelengths of the intermediate colors decrease in length progressively from the red to the violet, and of course, the frequencies of their vibrations increase in the same order. All sunlight is made up of these rays of different colors and different vibration frequencies, and of other rays as well, to which the human eye is not sensitive, and which therefore do not appear in the visible spectrum. Among these invisible rays are the infrared rays, which come just below the red of the visible spectrum, and which are of a longer wavelength than the red rays, and the ultraviolet rays, which lie beyond the violet rays of the visible spectrum, and are of shorter wavelength than the violet rays. Now, a ray of ordinary sunlight is separated into the rays of various colors, which form the solar spectrum, when it passes from a medium of one density obliquely to a medium of another density, as when it passes from air to glass, or from air to water, or from outer space into the Earth's atmosphere. Under such circumstances, its velocity is slowed down when it passes from a rare to a denser medium, and the waves of different wavelengths are bent from their former course or refracted by different amounts. The red rays of longest wavelength are bent from their former course the least, and the violet rays of shortest wavelength are bent the most upon passing from a rare to a denser medium. As a result, the ray of sunlight is spread out or dispersed into its rays of different wavelength and color upon entering a medium of different density. It is this refraction and dispersion of sunlight that produces many color effects in the Earth's atmosphere. The atmosphere is not of uniform density throughout. At high altitudes it is extremely rare. That is, there is little of it in a given volume. Close to the Earth's surface, however, it is comparatively dense. Half of all the atmosphere is within 3½ miles of the surface, and half of the remainder lies within the next 3½ miles. We may consider it as made up on the whole of layers of different densities strongly compressed near the surface. Imagine a ray of sunlight entering the Earth's atmosphere from without. If it comes from a point in the zenith, its course is not changed upon entering the atmosphere, because light passing from a certain medium, as space, into a medium of different density is not bent from its course or refracted, provided it enters the new medium in a direction perpendicular to the surface. If it enters the atmosphere, which is the new medium of greater density, obliquely, refraction or bending of the ray takes place, and as the ray advances toward the Earth through layers of increasing densities, it is bent from its former course more and more. As the advancing rays of different colors and wavelengths in the beam of sunlight are slowed down in the new medium, the red rays are turned from their course the least, and the violet rays the most, and the entire advancing wave front of the beam of sunlight is bent down more and more toward the horizon as it proceeds through the atmosphere. As we on the Earth's surface see the ray not along its bent course through the atmosphere, but in the direction in which it finally enters our eyes, the effect of refraction upon a ray of light passing through the atmosphere is to displace the object in the direction of the zenith or increase its distance above the horizon. As a result of refraction, we see the sun or moon above the western horizon after it has really set, and above the eastern horizon before it has really risen. The oval shape that the sun or moon often presents on rising or setting is due to the fact that the light from the lower limb is passing through denser air than the light from the upper limb, and so is refracted more. As a result, the lower limb is lifted proportionately more than the upper limb. This distorts the form of the solar or lunar disk, making it appear oval instead of circular. The familiar twinkling or scintillation of stars, and more rarely of the planets, is a result of interference of light waves due to irregular and variable refraction in air that is not uniform in density, owing to the presence of constantly rising and descending atmospheric currents of different densities. This also produces the shimmering or unsteadiness of star images in the telescope that interfere so greatly with accurate measurements of angles or observations of planetary markings. One may ask why it is, if light from an object, say a star, is bent from its course and separated into rays of various colors upon entering the Earth's atmosphere, that we do not see the object drawn out into a band of spectral colors. It is because the angular separation of the various colors is so slight under ordinary circumstances that light from one point is blended with light from a neighboring point of complementary color to produce white light again. Under certain circumstances, however, beautiful color effects may be seen in the Earth's atmosphere as a result of the refraction of sunlight. The blue color of the sky and its brightness is caused by the scattering of the rays of shortest wavelength, the violet and blue rays, by the oxygen and nitrogen in the upper atmosphere. The molecules of these gases interfere with the passage of these rays, powerfully scattering and dispersing them, and thus increasing the length of their path through the air, and diffusing their color and brightness in the upper atmosphere, while permitting rays of longer wavelength, the red and orange, to pass on practically undisturbed. When an object in the heavens lies close to the horizon, the rays of light from it have to travel a longer path through the atmosphere than when the object is overhead, and that too through the densest part of the atmosphere, which lies close to the Earth's surface, and in which are floating many dust particles and impurities from the Earth's surface. All these particles, as well as the increased density of the atmosphere, interfere with the free passage of the rays, especially of shorter wavelengths. The violet and blue rays are sifted out and scattered in their long journey through the lower strata of air, far more than when they come to us from an object high in the sky. Even the red and yellow rays are more or less scattered and bent aside, diffracted, by these comparatively large particles near the surface. The reddish color of the sun, moon, and even of the stars and planets, when seen near the horizon, as well as the beautiful sunset tints in which reds and pinks and yellows predominate, are due to the fact that the rays of longer wavelength are more successful in penetrating the dense, dust-laden layers of the lower atmosphere. It is to be free of the dust and impurities, as well as the unsteadiness of the lower atmosphere, that observatories are built at high altitudes whenever possible. When there have been unusually violent volcanic eruptions and great quantities of finely divided dust have been thrown into the upper atmosphere, the effect upon the blue and violet rays from the sun is very great. The volcanic dust particles are so large that instead of scattering these rays of shorter wavelength, as do the oxygen and nitrogen in our atmosphere, they reflect them back into space, and so decrease the amount of light and heat received from the sun. For this reason, the general temperature of the Earth is lowered by violent volcanic eruptions. Unusually cold periods that lasted for months followed the terrible eruption of Krakatoa in 1883 and of Katmai in 1912. At times when much dust is present in the atmosphere, the sky is a milky white color by day as a result of the reflection of sunlight from the dust particles. Sunrise and sunset colors are then particularly gorgeous, with reds predominating. At such times the blue and violet rays are almost completely shut out, and the red, orange, and yellow rays are powerfully diffracted and scattered by the dust particles in the air. The twilight glow that is visible for some time before sunrise or after sunset is, of course, entirely an atmospheric effect caused by the reflection of sunlight to our eyes from the upper atmosphere upon which the sun shines, while it is itself concealed from our view below the horizon. The atmosphere extends in quantities sufficient to produce twilight to an elevation of about 60 miles. When all the rays of which sunlight is composed are reflected in equal proportions, we get the impression of white light. Dust and haze in the air reflect all rays strongly and give a whitish color to an otherwise blue sky. Brilliant white clouds appear white because they are reflecting all rays equally. Clouds or portions of clouds appear black when they are in shade, or at times, by contrast with portions that are more strongly illuminated, or when they are moisture-laden and near the point of saturation, when they are absorbing more light than they reflect. At sunrise and sunset, when the light that falls upon the clouds is richest in red and orange and yellow, clouds reflect these colors to our eyes, and we see the brilliant sunset hues, which are more intense the more the air is filled with dust and impurities. The familiar and beautiful phenomenon of the rainbow is produced by refraction, reflection, and interference of sunlight by drops of falling water such as rain or spray. As the ray of sunlight enters the drop of water, which acts as a tiny glass prism, it is refracted or bent from its course and spread out into its spectral colors. Reflection of these rays next takes place, once or twice as the case may be, from the inside of the drop, and a second refraction of the reflected ray takes place as it leaves the drop. The smaller the drops, the more brilliant is the rainbow and the richer in color. The most brilliant rainbows are produced by drops between 0.2 and 0.4 millimeters in diameter. In addition to the primary bow, which has a red outer border with a radius of 42 degrees, there is the secondary bow with a radius of about 51 degrees and with colors reversed, the red being on the inner border. The supernumerary bows, which are narrow bands of red or green and red, appear parallel to the primary and secondary bows along the inner side of the primary bow and the outer side of the secondary bow. No rainbow arches ever appear between the primary and secondary bows, and it can be shown in fact that the illumination between these two bows is at a minimum. The primary, secondary, and supernumerary bows all lie opposite the sun in the direction of the observer's shadow, and the observer must stand with his back to the sun in order to see them. The primary and secondary rainbow arches take the form of arcs of circles that have their common center on the line connecting the sun with the observer, at a point as far below the horizon in angular distance as the sun is above the horizon. It is therefore never possible to see a rainbow arch of more than a semicircle in extent unless the observer is at an elevation above the surrounding country, under which circumstances it might be possible to see a complete circle formed by the rainbow. The highest and longest arch appears when the sun is on the horizon, and the greater the altitude of the sun, the smaller and lower the visible arch. As the angular radius of the primary bow is 42 degrees, and of the secondary bow 51 degrees, and as the common center of the two circles is always as far below the horizon as the sun is above, it is never possible to see either primary or secondary rainbow when the altitude of the sun is over 51 degrees, or the primary bow when the altitude is over 42 degrees. For this reason, rainbows are rarely seen at or near noon in mid-latitudes, since the sun is usually at an elevation of more than 42 degrees at noon, especially in the summer season, which is also the most favorable season for rainbows, owing to the great likelihood of rain and sunshine occurring at the same time. The light which comes to an observer from the primary bow is once reflected within the drop, and that which comes from the secondary bow is twice reflected within the drop. The sharper and brighter light, therefore, comes from the primary bow of 42 degrees radius. The space between the two bows is particularly dark because it can be shown that the drops there do not reflect any light at all. The rainbow colors are rarely pure or arranged in spectral order, owing to interference of light waves. It is the interference of light waves from different parts of the same drop that produces the bands of alternate maximum and minimum brightness that lie below the primary bow and beyond the secondary bow. The red or green and red bands of maximum brightness produced thus by interference are called the supernumerary bows, and they are always found parallel to the primary and secondary bow within the former and above the latter. The distance of the rainbow from the observer is the distance of the drops that form it. A rainbow may be formed by clouds several miles distant, or by the aid of the garden hose on our lawn. No two observers can see exactly the same rainbow because the rainbow arch encircles the surface of a cone whose vertex is at the observer's eye, and no two such vertices can exactly coincide. Two observers see rainbows formed by different drops. Refraction of light by ice crystals in clouds produces many beautiful color effects, such as halos of various types around sun or moon, vertical light pillars, circumzenithal arcs, and parhelia, sundogs, or paraselena, moondogs, which are luminous spots at equal altitudes with sun or moon, one to the left, the other to the right, at an angular distance of 22 degrees. The most usual form of halo is that of 22 degrees radius. This is a luminous ring of light surrounding sun or moon, with the inner edge red and sharply defined, and the spectral colors proceeding outward in order. Red is frequently the only color visible, the remainder of the ring appearing whitish. Since the halo is produced by refraction of light by ice crystals, which exist in clouds of a certain type gathering at high altitudes, it is always a very good indicator of an approaching storm. Coronas are luminous rings showing the spectral colors in the reverse order, that is, with the inner edge blue instead of red. They are usually of very small radius, scarcely 2 degrees, closely surrounding sun or moon, and are produced not by refraction, but by diffraction, or a bending aside of the rays as they pass between, without entering, very small drops of water in clouds. As in the case of refraction, the red rays are turned from their course the least and the violet rays the most. Many of these phenomena, halos, luminous spots, vertical pillars, and arcs of light, may at times be seen simultaneously when clouds of ice crystals are forming around the sun or moon. They then present a very complex and beautiful outline of luminous circles, arches, and pillars that have a mysterious and almost startling appearance when the cause is not clearly understood. We have found then that sunlight is made up of rays of many different wavelengths and colors, and that the atmosphere acts upon these rays in various ways. It reflects them or turns them back on their course. It refracts them as they pass through the gases of which the atmosphere consists, or through the water vapor and ice crystals suspended in it, thus sifting out and dispersing the rays of different colors and wavelengths, and producing beautiful color effects. It diffracts them, or bends them aside, as they pass between the fine dust particles and small drops of water in the air, again sifting out the rays of different colors and producing color effects similar to those produced by refraction. It also scatters and disperses, through the action of the molecules of oxygen and nitrogen in the upper strata, the blue and violet rays of shorter wavelength, and thus produces the blue color and brightness of the sky. It produces beautifully colored auroral streamers and curtains and rays of light through the electrical discharges resulting when the rarefied gases in the upper air are bombarded by electrified particles shot forth from the sun. It is our atmosphere, then, that we have to thank for all these beautiful displays of color that delight our eyes and give pleasure to our existence, as well as for the very fact of our existence upon a planet that without its presence would be an uninhabitable waste covered only with barren rocks. And with those thoughts of appreciation for our planet and the end of the chapter, I think we'll end this evening's reading from Astronomy for Young Folks, one of my all-time favorite books on this podcast. I have learned so much from this little volume, and I hope you enjoyed it as well. If you'd like to read this wonderful work for yourself, as always, you'll find a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect, suggest a boring book you'd like to hear read, or request more from one we've already started, you can drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.